Welcome back, everybody, and welcome to this new session on the machine learning course for the Erasmus Plus program. Now, the topic today, and also partly next week, is to discuss Lasso and ridge regression, which are modifications of ordinary least squares. One of the things which we discussed with least squares last week, the ordinary one, is that if we cannot invert the matrix, then we obviously cannot solve the problem and find the optimal parameters. So ridge and lasso regressions are ways by which we can avoid the problems with the lack of invertibility of the matrix we wanted to invert. However, this introduces additional parameters. So today, and this is the material which you find in both this week's slides. So what I'm displaying here is a Jupyter notebook for this week, but also from last week. So we need to go a little bit back to material which we didn't have time to cover last week. I will also use that to repeat some of the things which we went through last week. And then we are going to have a discussion of something which is called the singular value decomposition, which is a very important theorem in linear algebra, and which will allow us to even be able to invert matrices, even if they are not invertible. And another thing which is very important, it allows us also to discuss some mathematical aspects of both ordinary least squares, ridge and lasso regression, which hopefully is going to give us some more insights about the mathematics which we set up. And just to remind you, one of the reasons why we start typically a machine learning course with linear regression is that linear regression allows us to get some insights about the mathematics, which may be more difficult with the deep learning methods like neural networks. And this one of the reasons for that is that we have analytical expressions for the parameters, the optimal parameters. We also have analytical expression for the variance of these parameters, which means that we can link it immediately with a statistical interpretation. And furthermore, the second derivative of the mean squared error, which gives us a function which we last week called the Hessian. This is a function which we can demonstrate today with a singular value decomposition theorem, is that this is a function which leads to a convex optimization problem. And that is also extremely useful because it allows us to gain some insights about the mathematics of machine learning methods. And when we come to neural networks, we are going to have thousands and thousands of parameters, millions of parameters, and then it's very difficult to actually make this kind of mathematical analysis we do now. So in a way, linear regression and these methods like lasso and ridge regression, also kernel regressions, these can be seen as a kind of low-level machine learning methods, which allow us to gain some insights about the mathematics. Now, at the end of the slides this week, you will also find a set of exercises, which I recommend to take a look at. And I also wanted to ask you guys about the possible common meeting. And if you now look into the poll here, I'm just going to launch a short poll about a possible time for a common meeting. So take a look at it during the session here and just click on which fits best, whether we could do Saturday and Sunday, October 28 and 29, or whether you prefer in the afternoon of Sunday and Monday, like we are doing now. So that I know that you're busy with lectures during Monday. So what we typically have done is that we have tried to accommodate sessions for different groups of you. And if Sunday afternoon doesn't fit, we will just stay with Monday. Okay. So let's try, while you guys are clicking on the poll here, let's try to bring back the material which we had last week. I should also say that one of the reasons why I would like to meet towards the end of October is that then we can define the first project. And many of you last year had own data you wanted to analyze, so we can always tailor the projects to the type of scientific problems which you guys are dealing with, which to me is very important because that teaches me also a lot, because I learn from the kind of projects you're working with. And last year we had 5 of the groups which had their own data sets which they wanted to analyze in project 1. And then they actually reused the same data set in project number 2. And project number 2 deals essentially with neural networks and deep learning methods. So the course is split in 2 parts. So we will have the traditional pre-deep learning revolution methods for the first half. And then the second half of the course deals with deep learning methods like neural networks, convolutional neural networks, and recurrent neural networks. Okay, while you guys take your time and answer questions here, I'm going to set up what we did last week. So let me bring back where we were last week. And just as a reminder, at the end of the slides which you have for this week, you will find an exercise set. And these are also exercises which we can discuss together when we meet in the end of October. So I wanted to bring back what we did last week because we didn't finish properly last week. And the thing which we didn't was actually this part number 5, which is about region lasso regression and the singular value decomposition. I also wanted to remind you a little bit on how to prepare data. So the slides which you see here about centering data, taking out the mean value, and also scaling the data are important aspects in the preparation of the data. In particular, when we're now going to study Lasso and ridge regression, what we often end up with then is that we would exclude the intercept in the fit of, let's say, a polynomial, which means that if we do that, if we exclude the intercept, the hope is that we may get a better fit to the data, because sometimes the intercept can bring in a large bias on the optimization of a specific data set. So if we just scroll down here, the thing I wanted to remind you, besides this linear algebra calculations, which we also went through last week, I wanted to remind you of this quantity here, the Hessian matrix, when we deal with ordinary least squares. So with ordinary least squares, the derivative of the cost function, which we opted for, is now given by this quantity here, and that leads to a matrix inversion problem. Another thing which is also very important for us now is actually the second derivative. And as we will see today, this is a matrix which has positive eigenvalues only. So this x transpose times x. And when the matrix has positive eigenvalues only, which means it's so-called positive definite, then this leads to a convex optimization problem, and there is going to be a global minimum, which is very, very important. So that is an aspect which we will derive today when we now look at something which is called a singular value decomposition. The other thing which we went through last time was to split our data in training and test. This is a pretty common aspect, which is done in basically all machine learning training. And we would typically also, when we have lots of data, is to split the data in a validation set. And this validation set is normally done together with the training, which means that we validate the model and find the optimal parameters for a given model complexity. And then we use that on the test data. So the test data is never included in the training, obviously. So this is a data set which is just kept aside. If you scroll down more and more, we discussed pre-processing data and scaling and centering. So one of the standard types of scaling, which is also called centering, means that you subtract the mean value for each column in your design matrix. You can also do that on your output data, but it's pretty common to actually center the mean values by subtracting the mean values in the so-called feature or design matrix. The hope then is that this can lead to a better optimization problem. And in the codes here, we looked at different applications. We looked also on the scaling and the or the centering and the connection with libraries like scikit-learn, which do sometimes things by default for us. And I'm not going to repeat this, but I just wanted to highlight it and remind you of that. Now, one of the things which we then are going to do today is actually to add a constant or a term, which now depends on either the unknown parameter squared or the absolute value. And when we add that to the cost function which we had previously, which is the mean squared error, we are going to show that this gives us what's called ridge regression. And in ridge regression, it's common to actually leave out the intercept in the fitting in order not to penalize the fit by the intercept value. And the same is the case with Lasso. We are going to come back to that. Now, one of the things which we ended with was actually the mathematical interpretation of ordinary least squares. And we will stay with that a little bit today. And then we are going to move into the discussion of Lasso and ridge regressions, which then introduce a parameter, lambda, which allows us, hopefully, to tune the optimization process so that we may get a better mean squared error. But we are coming back to this. Now, one of the things which we also discussed last week was the mathematical interpretation of ordinary least squares. We found that the optimal parameters are given by this matrix inversion problem times the design matrix transpose times the output vector y. And the model which we designed then is then given by this design matrix times the optimal parameters which we have found. So this is the optimal model which hopefully reproduces our data here. Then we could show that if we now define a matrix which now contains these matrices here, this matrix is a matrix which squared is equal to itself, and that defines a projection operator. So, or a projection matrix. That means that this matrix A acting on the output data projects out the output data. So you could say that the model which we have can be represented by an orthogonal projection of y onto a space which is defined by the column vectors of x. And in our case here, the matrix A is a square matrix. And if it's a general rectangular matrix, we have what's called an oblique projection matrix. And then you can look at the residual error, which is actually the difference between your output and what the model is making. And then you will see that this is the same as the orthogonal component of the space defined by the column vectors of x. And a very useful test when you're writing your code is actually to assume that x is an orthogonal matrix. If x is an orthogonal matrix, then we have this property that x transpose times x is equal x times x transpose, and that's equal to the identity matrix. In that case, this matrix A is simply equal to the identity matrix. And then you have the obvious case that your model gives a perfect reproduction of your data y. And that is always a useful test of your machinery, just to see that that is the case. Now, the thing which we started with last week was this important theorem in linear algebra, which is called the singular value decomposition theorem. We are going to state it here. We will not derive the theorem, but we are going to use it. And one of the reasons why this becomes important is that if you look at this matrix x transpose times x, if we go back a little bit here, if this matrix which we want to invert is singular, then what happens is that obviously we cannot do anything. Now, one of the cheap tricks which was used in the 60s and 70s was actually to add just a small constant, something like 10 to the minus 8 or 10 to the minus 7, to the diagonals of this matrix. when you add a small constant shift to the diagonal matrix elements, then this matrix becomes invertible. That is a trick which has been used in many times. So what you would have then would be this matrix here plus a constant lambda multiplied with the identity matrix. And then you would invert a different problem, which would always be invertible. Now, doing that is something which leads to what's called Lasso regression, where we would simply add a term like this one to the mean squared error, which we discussed last week and the week before. So you can actually give this cheap trick where you just add a constant along the diagonals. You can rewrite that in terms of an optimization problem, which now contains an additional function. And we are coming back to that because that leads to ridge regression. So I just wanted to say something quickly about the singular value decomposition, because it says the following. Even if the matrix is singular, that means you have at least one eigenvalue which is 0, or it's non-invertible, you can always singular value decompose the matrix. And the singular value decomposition exists always. And that is an extremely powerful theorem, because you can use that one on the type of problems which we have here. And the type of problems which we have deals actually with the matrix invertibility. So just to give you some of the mathematics before we move on, and I'm going to use the slides a little bit before we move on to the whiteboard. So one of the typical problems you encounter with this linear regression, in particular if this matrix is high dimensional, are problems with near singular or singular matrices. And the column vectors may be linear dependent, and this is normally called supercollinearity. So that means that you can basically not invert the matrix. And the columns of this, if you look at this specific example here, they're actually linearly dependent. And you can see that since the first column is the row-wise sum of the other two columns. So that means that the rank of a matrix is the dimension of the space spanned by the column vectors. So this matrix here, instead of being of rank 3, is actually a matrix of rank 2. Another matrix which you may encounter, which looks pretty innocuous, is actually this square matrix here, which has, when you calculate the determinant, you see immediately that has a determinant 0. So that means that the matrix is singular and the inverse is undefined. This is the equivalent to saying that the matrix has at least an eigenvalue, which is 0. So we can always cheat and simply take add a constant along the diagonal, and which would be positive, and then we would simply be able to invert the matrix. So as I say here, the simplest trick which has been used is actually to do this. And you will see in numerical codes from the 60s and 70s that people would often add something which was labeled as 0, but which is non-zero, in order to avoid problems of round-off errors and loss of numerical precision. But here it was simply added in order to be able to invert the matrix. Now, when we now come to ridge regression, this lambda becomes a parameter we can tune. So one of the things which disappoints many of you when you start with machine learning is the amount of parameters which you can tune in order to get a better fit to the data. Now, by adding this parameter here, we will actually get an addition to the cost function, or the objective function as we called it, and then we can basically then enter a problem where the matrix to invert is actually invertible. And tuning this lambda can actually lead to a smaller mean squared error, which is also very interesting for us. And the thing we have to face is that in general, the matrix which we set up, the design matrix, may have strong dependencies. So we've been looking till now at simple problems when simple problems, what I mean is this kind of vanilla types of problems where we make a polynomial fit. And when we make a polynomial fit, each column represents a degree of the polynomial. So that will be a first order, second order part, third order part, and so on. And these will be vectors which in general are independent of each other and in principle orthogonal to each other by almost construction. And that means that when we do a polynomial fit, we often never encounter problems with singularities. However, if we look at real data, if you take, for instance, a famous data set on tumors, on cancer data, then each column could represent specific features of the tumor. And one of the features is actually the area of the surface of the tumor. And another one will be the radius of the tumor or the diameter. And clearly these two quantities have to be connected. And other parameters could be the thickness of the tumor, etc., etc. So in general, in such a data set, there is a large possibility for correlations among the data sets and also dependencies, which means that when we are going to try to invert the matrix, we will have problems with singularities. So as I said, one cheap way to fix the singularity, just to do that, but we can, what we will show today is that we can rewrite this in terms of ridge regression, which gives a slightly more elegant mathematical connection to the optimization problem, and a nice connection with a probabilistic interpretation of ridge regression. So I'm going to go back to the whiteboard, and we are going to look at the singular value decomposition. So the singular value decomposition, what it says is that a matrix, like this matrix which you see here, this explicit matrix, which is not diagonalizable, which is also called a defective matrix, is a matrix we can decompose by a singular value decomposition. And what we get then is a matrix. So since this is a 2 by 2 matrix, we get an orthogonal matrix U of, in this case, dimensionality 2 times 2. We have the matrix sigma, which now contains the so-called singular values. And these are ordered so that the first one is larger than the next one, etc., etc. And in this specific case, we have a singular value, which is 0. And this reflects simply the case that this matrix has an eigenvalue, which is 0. So you can see from the singular value decomposition how many eigenvalues are actually equal to 0. And then we have a matrix V, which is also an orthogonal matrix. And the interesting thing with the singular value decomposition is that it always exists. Now, what I wanted to use now is actually the singular value decomposition in order to make a further analysis of ordinary least squares. And then we are going to introduce ridge regression, and we can use the same type of analysis to understand what ridge regression is actually doing for us. So let me switch back to the whiteboard. And guys, feel free to ask questions before we move on here. So much of the material here is something which I will actually cover now by the whiteboards. So what we are going to look at now is actually our problem, which we have, the design matrix, where we now have ordered it in terms of different column vectors. And these column vectors can represent some specific features. So if you're doing a polynomial fit, each feature represents some polynomial degree. And alternatively, if we have a function, set of functions, there could be sines and cosines, etc., etc. So let's switch to the whiteboard here, and then look a little bit closer at the analysis. So what we're going to do now is a so-called singular value decomposition of the design matrix which we have here. I have a small problem with my pen, so let me just fix that one. Just a moment. I'm just going to do a small thing here because I see that my pen didn't connect with the whiteboard. So just a small moment, and let's go back to the slides while I'm connecting my pen with the whiteboard. Okay, now it should be done. So let's connect the whiteboard again. So the SVD analysis of ordinary least squares, and we should also add ridge regression, but let's do the ordinary least squares before we start with ridge regression. So what we have defined is a design matrix, or feature matrix as we call it. And we design this one as a matrix of dimensionality n times p. And n is the number of data entries which we have, and p is the number of features which we have. So if we're dealing with this tumor data I mentioned, typically that data set has something like 30, 40 features, which a pathologist may recognize as important features to classify a tumor, whether it's a benign or malignant. If we're doing a polynomial fit and we do a polynomial up to the degree of 9, then we would have, with the intercept, we would have 10 parameters. So that means that p would be equal to 10. So the matrix which we had, this x, is something which we can then rewrite in terms of an x00, x01, and we start with 0 because this is where Python arrays start with. So this will go up to p minus 1 here. And then I have x10, and then we have the xn minus 1, 0. And then finally we have xn minus 1 of p minus 1. And we can rewrite this in terms of a set of vectors. So we can rewrite this. So this is a design matrix, and we have x0. So this is now a vector, x1, x2, up to xp minus 1. So these are the vectors which now represent the matrix. Now, when I do the singular value decomposition of that specific matrix, I can actually rewrite that in terms of these orthogonal matrix U. I have this matrix with the singular values. They're called the singular values of the matrix, and they are organized as a descending set of singular values. And I have this orthogonal matrix V. So U times U transpose. So since these are orthogonal matrices, this is given by the identity matrix, and the same applies to V, and that's equal to V of T of V, and that's also equal to the identity matrix. So the matrix U has dimensionality of n times n. The matrix V has dimensionality of p times p. So that is normally a matrix of a smaller dimensionality. And we have chosen normally here n to be larger or equal to p. It's pretty common actually to have n much, much larger than p. Okay, so the matrix sigma is then the matrix which contains the singular values. So this matrix sigma now is a matrix which contains the singular values, sigma 0, sigma 1, up to sigma p minus 1. So these are the values which are non-zero. And then we have values which are 0. So the only matrix elements along the diagonal. And sigma has a dimensionality of n times p. And the rank of the matrices will then be defined by the number of non-zero singular values. So this sigma 0 is normally larger than sigma 1. You can define this sequence of numbers in a different way. and this is larger than sigma p minus 1, which is normally larger than 0. So this is a standard way of setting up this type of problems here. So as an example, we could now look at a specific matrix. So let's do that. So one matrix which we could think of as a sigma, just as an example, is a matrix which has a dimensionality 3 times 2. And we have a sigma which now has values 2, 0, 0, 1, and then the reminders are 0. That's an example of such a matrix. And we see now that if I calculate with this specific matrix, if I calculate sigma transpose times sigma, that is going to be a matrix which has dimensionality p times p. On the other hand, if I calculate sigma times sigma tau, not sigma tau, but sigma transpose, this is a matrix which has dimensionality n times n. And if I look at this simple example which I have here, you will now see that if I perform these operations, these matrices are going to give us, one is going to give us, if I take the first one here, for this specific example, this one, that is going to give us a matrix where I have 4, 0, 0, 1, for this specific example. And then the other matrix will have 4, and then it will have 1, and then it will have 0 along the diagonals. Now, why do we care about this? Now, one of the reasons is that this allows us to make some nice interpretations of ordinary least squares and this ridge regression, and to get an understanding of their differences. So let's take a look at one quantity here now. And one of the things which we saw last week, just to remind ourselves of that, is that the second derivative of d beta transpose, this is given by this quantity we call the Hessian matrix. So the second derivative of the cost function, this becomes important when we are now going to look at optimization and gradient methods, which come a little bit later, not next week, but the week thereafter. So what we have then is x transpose times x. So let's take a look at x transpose times x and use a singular value decomposition on that and just see what we get. So if I use the singular value decomposition, because every matrix can actually be singular value decomposed. So this is obviously given by this quantity, and then I have u times sigma of v of t. So that gives us a v times sigma transpose times u transpose times u times sigma times v of t. So if we then use the orthogonality, we know that this has to be equal to 1. Then what I'm left with is v times sigma t times sigma times v of t. So if we now look a little bit closer to this expression, and we multiply from the right with v, what we get then is that x transpose times x multiplied with v. So v is now a matrix which has orthogonal vectors. We're coming back to that. Then what we get is v times sigma t times sigma. And this is given by v transpose times v. And that's the same as v times sigma t times sigma. Now, if you now go back to what we had previously, this is a matrix which has dimensionality p times p, but it has only diagonal elements. And this is a matrix of dimensionality p times p, but it contains these singular vectors, or just the vectors, the orthogonal vectors of the matrix V. So keep in mind that this matrix V contains now orthogonal vectors V0, V1, V2, up to V of p minus 1, with the properties that V of I transpose, the inner product of V of j, is actually delta ij. So if I now look at what I have here. So I have my design matrix, actually the second derivative of the design matrix, multiplied with V, which is a set of orthogonal vectors, which is now equal to this V. And when I'm now setting it up here, I have sigma 0 squared, sigma 1 squared, down to sigma p minus 1 squared. So these are just eigenvalues. And then if I pick one specific component, V of I, what I see then is that this sigma t, x transpose times one of the eigenvectors is actually equal to V of I multiplied with sigma I squared. So that means that the eigenvalues of this matrix x transpose times x are the singular values of x, the design matrix, and they are given by sigma I squared. These are the singular values with eigenvectors V of I. Why is this interesting? Well, we have defined the sigma i's are all larger than 0. And even if they had not been larger than 0, we know that the sigma I squareds have to be larger than 0 because we are assuming that these are real numbers. So that means that x transpose times x is what we call a positive definite matrix. And that leads again to a convex optimization problem and the existence of a global minimum. So this is just something I'm stating as a result from linear algebra analysis, but we can actually show, we have shown now that the eigenvectors are positive. If you have only a scalar function, then clearly you have that the second derivative is larger than 0. But since this is a matrix, x transpose times x, and not a scalar, then we end up with a matrix which is now positive definite. So x transpose times x is a positive definite matrix. Which leads to a convex optimization problem and the existence of a global minimum. So we have now shown that this part of the analysis allows us to say something about the design matrix itself. Now, there's another important feature which we are coming back to, and this deals with statistics, and that is that this matrix x transpose times x multiplied with 1 over n, that is the same as the covariance matrix, and we are coming back to that when we deal with a statistical analysis. So this is the covariance matrix, which is also a very important property here. Now, what we've showed now is that the matrix x transpose times x is actually a matrix which has eigenvectors given by the orthogonal matrix V, and it has eigenvalues as the singular values squared. So these are very useful properties. Now, we are going to use this also to interpret the ordinary least square method with ridge regression. But let's now just add for completeness the case with completeness. If we now look at x times x transpose and perform a singular value decomposition of that, what we need to keep in mind then is that this is now a matrix which has dimensionality n times n. The matrix which we decompose then in terms of the singular value decomposition is then given by u times sigma times v of t. And then I take the transpose of this matrix. So what I get is v times sigma t times u of t. And that is the same when we use the orthogonality of these matrices. This becomes equal to u times sigma t times u of t. And then we multiply from the right with the matrix u. So what we get then is that x times x transpose times u is now equal to u times sigma t here. Now this matrix here will also contain zeros. So that's going to be equal to this u multiplied with sigma 0 squared, sigma 1 squared, and then at some place we are going to get a series of zeros, which we did not have in the previous case. Now, if you then remember that u is a matrix which contains orthogonal vectors, then we have u0, u1, u2 up to un minus 1. And that means that now we can actually write new eigenvalues. So if we do that, this means that we will also have some eigenvalues which can be 0. And that reflects the fact that our matrix could be singular. So we cannot escape in a way the singularity of the matrix which we start with. So if we then take x transpose and multiply that with any of these vectors, this is going to be given by sigma I squared times u of I, where now sigma I goes from sigma 0, sigma 1, up to sigma p minus 1 squared, but then I will have zeros all the way up to n minus 1, which is the full dimensionality. So if we have more than one singular value, when we diagonalize this matrix, or the matrix X, then what we have is a set of, so these sigmas are actually the singular values of the design matrix. Okay, so any questions so far? These were just some mathematical exercises. The thing which is important for us now is actually to look at the expression for ordinary least squares. So let's take a closer look at ordinary least squares now. So what we have in the ordinary least squares, we're going to use this in order to make an analysis of the ordinary least squares method. So let's take a look at the way we would write out the parameter beta. So this is something which goes like x transpose times x minus 1 times x transpose times y. Now the model which we create then with these optimal parameters is equal to x times beta optimal, which again is the same as x of x transpose times x minus 1 times x transpose times y. Now, what you can show then, and this is part of the exercises which you find at the end for this week, we can now write this in terms of the singular value decomposition. So this will be given by the matrix U times sigma times V of t. That's the first part here. And then we have the matrix to invert, which we calculated on the previous page. And this will be given by, if we go back here, we know that this matrix, when we singular value decompose it, is going to be given by this quantity here. So I can insert that in the denominator for the matrix to invert. So we are going to have to invert V times sigma times, so if we go back and just keep in mind that expression, so we have V sigma transpose times sigma times V transpose. And then we have V transpose. And this is now multiplied with V. We have the inverse of this matrix. And then we have V times sigma transpose times UT transpose times Y. And now you may ask, where are we going here? Now, there is an interesting thing here. And this is something which we now have to be a little bit careful with. So in order to rewrite this matrix, we need now to use a theorem from linear algebra, which is actually going to be very useful for us, because the quantity which we have in the denominator here is actually an invertible matrix. And let's see why. So if assume that you have two matrices, and this is where we're going to stop before we take a break. So you have a matrix A and B, and these are square matrices. And both are invertible. But keep in mind now that the V is a matrix which is orthogonal. So that means that V of t, the transpose of that one, is the inverse of the matrix. So the matrix V, by construction, through the singular value decomposition, is an invertible matrix. Now, the other thing which we have is that sigma t times sigma contains only these singular values, which are all non-zero. And these are diagonal numbers. So what we have then are actually a set of numbers which are given by diagonal matrices. So this sigma of t is also invertible. And it is a square matrix because it has dimensionality p times p. So when I now look at a very important property with invertible matrices, so if I look at this property here with two matrices, if they are square matrices and invertible, and both our matrices V and sigma transpose and sigma are invertible matrices, if I do that, this can actually be rewritten as the inverse of B multiplied with the inverse of A. And keep in mind also that V of V transpose is equal to V transpose times V. So we know that that is an invertible matrix. So what happens then is that I can rewrite my denominator. So this V of sigma transpose times sigma times V transpose, inverse of this quantity, that can actually be rewritten in terms of V t minus 1, and that is just the matrix V again. And then I have sigma t times sigma inverse and multiply with V minus. And if I do that, then what I'm getting is V multiplied with sigma t, sigma of inverse, multiplied with V of t. So this becomes now still a matrix of dimensionality p times p, but I can actually now put that back into the expression for y, which contains x, the matrix x, times this denominator. So what I have then is u times sigma times v transpose times v. And now I have this denominator sigma t of sigma minus 1. And then I have v of t times v. And then I have sigma transpose times u transpose multiplied with y. So I use the unitarity or the orthogonality of the matrices. So these are just given by the identity matrices. And then I'm having u of sigma. And then I have to take the inverse of this quantity. I have to be a little bit careful when I do this now, and this is something which we will discuss after the break. Why? Now, after the break, we are going to look at the dimensionality of this problem, and what we are going to show then is that y is going to be given by a sum over j equals 0 up to the number of features, and this is smaller than the number of n. And this is going to contain the vectors of u of j transpose multiplied with y. But this is a topic for after the break. I went a little bit over time. I hope you can excuse me a little bit. Feel free to ask questions. because we are going to use this in the analysis of the difference between ridge and lasso regression. So let's take a small break, if it's okay with everybody. So I'm going to pause the recording now. Thanks, first of all, to all of you who came with inputs about the time for possible meeting. So it seems that the week before or the week after, the dates which I propose seems to work better for everybody. So I will coordinate this with Francesca, and then I will send you an email about the optimal days. And then hopefully we can meet, all of us, and discuss in more detail some of the technicalities with exercises and the theory and the topics for the first project. Okay, so what I wanted to continue a little bit with before we switch back to the Jupyter notebooks and do some runs is to discuss the mathematical interpretation of ordinary least squares. And we are going to use much of these definitions here as well for ridge and lasso regression. So the hope is that this can give a kind of deeper mathematical understanding of what is taking place. So before the break, we showed that we could rewrite this equation like this. Now, there is a thing now we have to be a little bit careful with in the analysis. Because if you look at the expression we have here, it may look as if we can actually rewrite this one multiplied with that one and with this one as something which could lead to a unity matrix. And then we will simply have that y tilde, since we are then left with a term here which gives a unity matrix, and multiplied with this one and that one, and the orthogonality of the matrix U would simply give us that y tilde is equal to y itself. But that's not the case. And the important thing to keep in mind is that when we perform these multiplications here, the dimensionality of this matrix, sigma transpose times U, becomes a matrix of dimensionality p times n. And when we perform this operation here, we will only keep those vector components of U, which then represent the non-singular values, or the values which are non-zero. So let's take a look at that. So the expression which we have for y tilde, the model which we have, is now given in terms of the vector, the matrix U multiplied with sigma. And then we have this matrix sigma t times sigma and the inverse of that one, multiplied with sigma transpose, multiplied with U transpose, multiplied with Y. So this sigma, the matrix sigma, contains the singular values. So it has sigma 0, sigma 1, and down to sigma p minus 1, and then we have the zeros. And it's a matrix of dimensionality n times p. Now the matrix U contains now the column vectors U0, U1, U2, up to U of n minus 1. So when I take this matrix sigma transpose times U transpose, that is going to be a matrix of dimensionality. Since I'm now taking the transpose, I will have p times n. So it's going to be a matrix of dimensionality p times n when I do the calculations. So what you will have then, when you're looking at the calculations here, is that the product of this matrix sigma transpose times U transpose will have a constant given by these sigma values multiplied with the vectors U0, U1, but UN minus 1 will disappear. So what we will end up with when we perform that calculation here is a new matrix. So this sigma t times u of t is going to be given by a matrix which now has sigma 0, and then I have u0. And now keep in mind that every term u0 has length n, but then I end up with sigma 1 of u1, and this terminates at sigma p minus 1 of u of p minus 1. These are the only non-zero components. You can easily see that if you take the simple matrix. So one thing which I recommend you, if you're a little bit in doubt, if we go back to that simple example we had before the break, suppose we take this matrix which you see here, and we take the transpose of that one. So let's just look at that and what kind of result we will get then. So let's take this matrix and perform the transpose of that matrix. So what we will have then, if we take this matrix and transpose it, so let's just put up this matrix sigma, which we defined as 2, 0, 0, 1, 0, 0. When I transpose this matrix, then what I obviously will get then would be 2, 0, 0. And then I have 0, 1, 0. And then I'm going to multiply this with a matrix U. And this matrix U is now given by U, the vector U0. It's a matrix of dimensionality n times n. And since we have a free vector, so in this case, n is going to be free. So I will have U0, 0, U0, 1, and U02 here. I will have U10 and U20. I will have U11, U121, and then I have U12 and U22, which is the same as U0 times U1 and U2 here. These are the vectors which we have. And when I transpose it, what I obviously get then is the transpose of that matrix. And when I perform the multiplications now, what you will see is that the vector u of 2 will disappear, because that will be multiplied with values which are 0 here. So u2 here disappears in the calculations. So when I perform these operations, what I actually get is a quantity which looks like this. So that means that when I multiply this one again with this quantity, which is a matrix of dimensionality p times p, and I multiply this quantity here, which is a matrix of dimensionality n times p here, what I will get then is just a contribution from the non-zero components. And that means that when I now set up everything, you will get that y tilde can be written out as j equals 0 up to p minus 1, and then I will have u of j transpose times y. If I had had the sum from j equals 0 to p to n minus 1, and remember now that p is assumed in our case to be less than n or equal n, then I would have ui ujt, if I have the full case, times y. This is the same as u times u of t. These are outer products, just keep that in mind. So u times u of t is a matrix. So what it's doing now, it's a matrix which projects out components of y. Then in that particular case, I would just have gotten y. If we are making the sum over up to n minus 1, because u is an orthogonal matrix. So what we have now, if we look at this expression here, this one, this is a projection of y in terms of the orthogonal vectors ui, but summing up only, but including only the non-singular terms, or the singular values which are different from 0. The singular values different from 0. So you can think of this in terms of the singular value decomposition, as we also did in the previous analysis from last week. We can simply interpret ordinary least squares as a projection using these orthogonal vectors of the original dataset Y. And clearly, if we have a full orthogonal transformation, then Y tilde will be exactly equal to Y. This is normally never the case. Now, the reason why we do this is that this is going to give us a very nice connection with ridge regression. So what I'm going to do now is to bring back what we discussed with ridge regression. So if we now look at the matrix X transpose times X, when it is singular, then we cannot invert it. And a common trick is then to add just a value along the diagonal matrix elements, because then the matrix will be diagonalizable and invertible. When it is singular, we cannot invert. So the cheap trick is to simply add a positive small constant which we call lambda to the diagonal ones. So remember now that this X transpose times X has dimensionality P times P. So what I do now is simply I add, if I do X transpose times X plus a constant lambda, a small number, and then I put in the diagonal matrix, which now has dimensionality P times P, then the problem is invertible. And by this simple trick, what I would get then would be Y tilde, which is equal to X. And this is now given by X transpose times X plus lambda of Y. And now I skip this P times P because it's understood that that is a dimensionality. Remember again that X has dimensionality N times P. So we have an N times P matrix, which is multiplied with a P by P matrix. So that is all okay. And then I have X transpose times Y. So this is a problem which we are setting up now. And when we do this, this matrix is now suddenly invertible and all problems seems to be solved. Now, this is not very satisfactory. And in a way, this was what was done in previous years, back in the 60s and 70s, in order to invert the matrix. But we can actually define a new cost function, objective function, which includes a so-called hyperparameter. It's normally called a shrinkage parameter, and you will see quickly why this is a shrinkage parameter. So let's take a look at the next way of defining the objective function. By the way, I should also mention one thing before we move on to that. If you now look at the expression which we framed in here, we see now that there are degrees of freedom which have been removed, because the sum here stops at P minus 1. This means that there are specific degrees of freedom here which do not appear anymore. So what you would say now is that this represents some effective degrees of freedom, because we have taken away some of the degrees of freedom from the full problem. And these degrees of freedom are the degrees of freedom which correspond to the singular values being 0. But let's now look at ridge regression. So ridge regression, this is the first extension of ordinary least squares. So what we're defining now is a cost function which contains the standard mean squared value. This is also called an objective function or a risk function or loss function, etc. So many different names. And in our case now, this is going to be given by the mean squared error, which we had before. So I'm going to keep that one. Keep in mind also that sometimes people would skip the factor 1 over n. I will keep that factor. And then we have I equals 0 up to n minus 1. And then we have the data points, the outputs, which we want to reproduce. And then we have the sum over the parameters, so p minus 1 of xij multiplied with beta j squared. But now we add a new parameter. So the new parameter goes like plus lambda. And then we rewrite that one in terms of a sum of j equals 0 to p minus 1. And then we have a beta j squared. This is often written in a more compact way. So you will see that often written out as the expectation value, the mean squared value, or in terms of this vector matrix notation, which we've been using, x times beta transpose times y minus x times beta. And then I have plus lambda. And you will often see this being rephrased in terms of a norm of a vector. And you will see it rephrased in terms of 1 over n. So this is called the norm 2 of a vector. And it's squared plus lambda times the norm 2 of this vector squared. So the norm 2 of vector, just to remind you of that, x norm 2 here is simply the sum over the square roots of the matrix elements. So this will be the sum over I 1 up to n of xi squared. So this is the definition of the norm 2 of vector. And this is an equation which we now can optimize in the same way as we did before. So if we do that, we are going to get something which looks pretty similar to what we had before. So let's take a look at now the optimization problem. So if I take and optimize dc d beta of this specific function, what we are going to get then is obviously minus 2 divided by n. And then we have x transpose times y minus x times beta, the unknown parameter. And now we have to be a little bit careful because what we have is this term beta here. So we have the vector beta squared. So we're going to get a term which goes like 2 times lambda times beta. And lambda is assumed to be a parameter which is larger than or equal to 0. If it's equal to 0, then we just have ordinary least squares. Now, what I'm going to do now is obviously to divide away the 2's here, and I multiply away the n. So that means that I get a lambda times n, which I'm going to call a lambda tilde, which I'm then just going to relabel as a lambda. This is just a parameter. So I multiply away the factor of n, divide away with 2 here. So what we're going to get then is minus x of transpose times y minus and plus. So we have x transpose times x times beta plus lambda times beta. And now I collect the terms. And then what I get then is that the optimal beta is going to be equal to the matrix which I now have to invert, which is x transpose times x plus lambda times the identity matrix. and this is the one I want to invert, multiplied with X transpose times Y. So obviously we want this to be 0. So this is the quantity we actually want to zero out. And this is the expression for ridge regression. And what you see now is that we have introduced a new parameter. So lambda is a so-called hyperparameter, which we can tune. And you can actually show that the mean squared error, which you can get, can actually in some instances be smaller than the one you would get when you now perform an ordinary least square. It's also called a shrinkage parameter. And we will see quickly why this is a shrinkage parameter. In one of the exercises, you're actually asked to perform the same analysis which we did with ordinary least squares. That means this analysis here. So it's actually not so difficult to repeat that analysis. And I'm going to give that as an exercise. So you will find that at the end of the weekly material for this week. So we can show so this is exercises at the end of the material for this week. So we can then show that this y tilde, which we have, is now going to be given by a sum from j equals 0 to p minus 1. But now we are going to have the singular values. So we will still have these vectors, uj, ujt, which project out. But then we are going to have a sigma j squared divided by a sigma j squared plus 1. And this is now multiplied with the vector y, the original one. So we see now that plus lambda in here, we see now that when lambda is large, what happens then is that we shrink the contribution from a specific value sigma j or j. Contribution from a given component j. Now, there is a simple example which we're going to use to actually show this now. In order to understand it, let us look at a simple example, because then you will see pretty clearly what the ridge regression is doing mathematically. So the expression which you see here is the one you can show in one of the exercises, and the derivation is basically the same as we did for ordinary least squares, except that now we get this additional term. Now, one thing you see is that if sigma j is small, then the effect of a large lambda is going to be more important compared to the case when sigma j is large. Later, we are going to show that this parameter sigma j and this parameter lambda, when we introduce a probabilistic interpretation, a statistical interpretation of ridge regression, we are going to see that this lambda can actually be interpreted as something which is proportional to the variance of the parameters beta. But we will come back to that a little bit later. So the nice thing with these expressions is not only that we can use plain linear algebra to get an understanding of what happens. So we are actually reducing the importance of some of the parameters, and that's why this is called a shrinkage parameter. And we will see specific applications of that next week and the week thereafter. And the thing is that by doing this, by summing over only specific components, we are reducing the number of degrees of freedom. And at the same time, we are driving some of them to 0 if we make lambda big. If lambda is equal to 0, then we just have ordinary least squares. So let's look at an explicit example in order to understand what happens. And now we're going to make a very simple case, but this simple case contains a lot of the basic information here. So what we're going to do now is simply to assume that the design matrix is 1. And then we are going to assume that y is then obviously equal to beta, right? Because the design matrix is the identity matrix. That means that if I look at ordinary least squares, then my function is just given by the mean squared error. So that is the sum over 1 over n. And I'm also assuming now that n is equal to the number of features which we have, just to make life simple. So I have a sum over 1 over n, and this goes up to n minus 1, which is the same as p, y of I minus beta of I squared. So this is my model now, because I have made a model where y tilde originally is given by x times beta. So this simply becomes beta here. And if I now take the minimization here, if I minimize with respect to beta, what we find then is obviously that y of I has to be equal to beta of I. This is pretty easy to see. If I do ridge regression, on the other hand, then we have a new cost function. So I have my C of beta, which is equal 1 over n, and then I have a sum from I equals 0 to n minus 1, and then I have my y of I minus beta of I squared, and then I have these parameters lambda plus I equals 0 up to n minus 1, because p is equal to n, and then I have beta I squared. And then I take the derivative of this quantity. So if I take the derivative, let's do that. But let me wait till you guys have been able to write it down here. So if I take the derivative, what I get then is a dc of d beta of I, and I want that to be 0. So that becomes minus 2 divided by n, and I have my y of I minus beta of I plus 2 lambda of beta of I, and we want this to be 0. And we multiply away the number of number 2's, and we multiply away n, redefine lambda, and then just relabel it as lambda, because this is just a constant. Then what we find is that beta of I for ridge, the optimal value, is simply equal to y of I 1 plus lambda. So we can make a simple plot of this now. So if I plot y of I as a function of beta of I, and I have plus 1 here, minus 1, and minus 1 here, and plus 1, then we see that the ordinary least squares just gives us this straight line. So this is ordinary least squares. But then if I do ridge regression, what I will get then is something which goes like this, depending on the value of lambda. So this is ridge. So the parameter lambda, what it is doing for us, it is reducing the, so this should actually cross 0. So my drawing skills, as you can see, they are not the very best ones. It should cross 0 here. So what you see is that the ridge regression, ridge shrinks. The beta I values. In this case, it does it for all of them, and all of them are the same. They're just equal to the data points y of I. So this is a kind of a simple case, but which tells you what we may expect then when we perform a optimization with ridge regression. So if you go back to the equations here, what will happen when you run a ridge regression? If you look at the function which we have here, what happens then if you shrink these parameters to close to zero? The only thing which survives in the cost function and in the calculation of a mean squared error would just be your data points. And what you will see then is that your ridge regression reaches a plateau where the value is simply given by a mean squared error, if you're calculating that one, which is just given by your data points. But it serves as a useful way, and you can show that the mean squared error with the ridge regression can become smaller than the one for ordinary least squares. And the way to think of this now is that this gives you an additional parameter in the optimization. So you have more freedom to adjust your cost function to the data which you have. This is the way you should interpret it. And this term which you see here is something which people call a regularization term. So this is also another common name which you will see for this one. It's called a shrinkage term or regularization term. Or shrinkage term. Or other names. So in a way, you are now optimizing another function. And the hope is that by tuning these parameters, you can then get a better fit to, let's say, or a better fit to the data, and perhaps a better mean squared error. So keep in mind now that this function contains the mean squared error. So we are not only optimizing the mean squared error, but we are optimizing an additional function. So additional function which has this regularization term. This is pretty common to do in basically all machine learning methods. Now, there is another way to do that. Actually, there are many ways. And one of them is called Lasso regression. And I never remember what the acronym stands for. So in this specific case, what we have is a new function which still contains the mean squared error. But now it has the norm 1 of a vector. So it contains this parameter lambda, the shrinkage parameter, and it runs from J. And normally we don't include the intercept. We will come back to that a little bit later. But now it has the absolute value of J. This is often rewritten in terms of the norm 1 of this quantity, this norm 2 of the mean squared error. And it is squared. And then we have plus lambda plus the norm 1 of this additional parameter beta, which is the absolute value of the beta j's. Now, the problem we have now is that we cannot find an analytical expression for this beta of Lasso and the optimal value, like we did with ridge regression, where we simply have to invert a matrix, and ordinary least squares, where we have to invert a matrix. So in this particular case, the reason resides in the fact that when we take the derivative of an absolute value, due to the fact, if we take the derivative of an absolute value of d of x, we know that this one is equal to plus 1 if x is larger than 0, and minus 1 if x is smaller than 0. Now, this equation here has a discontinuity at 0. And what is often done in numerical implementations is that we just put that value to zero at zero. Now, mathematically, this is not exactly correct. But we end up with a optimization problem where we would now have a constraint, a condition on the derivative. And that means that since we cannot find an analytical expression, we would typically end up using libraries like scikit-learn in order to find these values here. So let's see what happens when we now go back to that simple expression, which we had before, this simple example, where we found that y tilde is given by the parameters beta. What we have then for Lasso is actually the following function. We have 1 divided by n, and then we have the sum over i's. We have y of I minus beta of I squared. But now we have a plus lambda, and then we have the sum over I here. It's the same sums. And then we have the absolute values of the beta i's. If I then take the derivative, what I'm getting then is a dc of d beta of I for one of the values. That's going to give us minus 2 divided by n. And then I have a y of I minus beta of I as before. But now I have a plus lambda, and then I have a beta of I divided by the absolute value of beta of I. And this is a case where which now leads to an expression which is non-analytical in the unknown parameters beta. And we have to resolve this numerically. But in this case, we can actually find an analytical solution. And I'm just going to state it before we then stop today, because this tells you what Lasso is doing compared to ridge regression and ordinary least squares. So this simple example actually conveys most of the mathematics of what happens with Lasso and ridge regression compared to ordinary least squares. So what I will get with this simple example, that the beta i's with Lasso are simply given by a y of I, and it's not so difficult to show that, if this lambda, this y of I is larger than lambda divided by 2, I have a y of I plus lambda half if y of I is smaller than minus 1/2. Sorry, this should be lambda half, yeah. And then I have 0 if this y of I, the absolute value, is less than equal than lambda half. So if we bring back the figure which we had previously, we are going to get the following. So this would be, the straight line would be ordinary least squares. And then we have a ridge regression, which shrinks the values of the betas. So here I have my beta of I, and then I have my y of I. So this is my ridge regression. Now with my Lasso regression, what I get then is something which goes like a straight line. So these are schematic figures here. So it goes like a straight line up here, and then it zeroes out the value. So this would be minus lambda half, and then I have a plus lambda half here, and then the value will be 0, and then it grows again here. So this would be Lasso regression. So what we have done, in order to summarize, and then next week we are going to look at the numerical implementations of these methods. And if you take a look at the slides for this specific week, and I didn't have time to go through it because I wanted to discuss some of the mathematics here, what we have in the slides for this week is a set of examples where we play around with ridge regression and Lasso regression. So I would invite you to take a look at these, because I will start there next week and discuss some of the examples. And then next week, we are going to look at a statistical interpretation of Lasso and ridge regression. And that's going to give us, hopefully, a slightly deeper understanding of what these methods are doing. And then after that, after we've done the statistical interpretation, we are going to look at how we can use resampling techniques, and then the bias variance trade-off, and then we should essentially have all the elements which are needed to get started with the first project. So what we have are methods which simply now optimize another function, but we can still use this optimization problem to calculate the mean squared error. So the mean squared error is something we would calculate irrespective of method, because that's just a way to assess the quality of the model, one of the many ways. But now we are optimizing either this problem, and this gives us flexibility in changing the parameters lambda. And from this simple model, what you see now is that ridge regression shrinks the values compared with ordinary least squares when lambda is different from 0. Lasso regression, on the other hand, can shrink the value, but it can also drive some of the parameters to 0. And that means that it may actually quench parameters beta, which may have a large variation. And we will come back to that when we have the statistical interpretation of Lasso and ridge regression compared with ordinary least squares. And that will be the topic for next week. So in essence, we have used the singular value decomposition to analyze what ridge and ordinary least square regressions do. We have a mathematical expression for the shrinking due to ridge, but with Lasso, we have to solve everything numerically. So when we are going to implement Lasso, we will use a library like scikit-learn to do that. So coming back to the material which we have this week in the slides. So let me just bring up that one, because we didn't start covering that material well, but we have gone through the Lasso and ridge derivation. And this is a topic which I did on the whiteboard. I prefer to do that. You see the singular value decomposition here. And there are more interpretations, and you've seen this on the whiteboard. I also recommend, if you want to read more about the mathematics of ridge and Lasso, there is an excellent link to a paper by Van Wieringen. It's actually a set of lecture notes, 150 pages, and it's really useful reading. You will find the Lasso derivation, which we did here. And next week, besides this simple example, which you've seen here, we are going to look at some other examples. So we came to this yet another example case. And then we are going to look at more examples next week. And then we're also going to look at a statistical interpretation of Lasso and ridge regression. So feel free to take a look at the material here. And you will typically see when you make runs here, is that as a function of this parameter lambda, you're getting a mean squared error for ridge, which is small and will be the same as ordinary least squares. But then you drive the parameters beta to 0, and then it reaches a plateau here where the mean squared error now just is your data points squared, as we discussed. So take a look at these examples to next time. There's also a link with the rescaling of data, which becomes important, which I wanted to say something about, because in ridge regression and Lasso regression, it's common to leave out the intercept, because the intercept can be large, and you won't avoid your optimization to be penalized by a large parameter. And it's common then to just leave it out. And this has some consequences for the way you implement it using libraries and your own code. Then there are some exercises, and these exercises deal essentially with what we've been looking at here. So it's you deriving ridge regression, and also to perform the singular value decomposition, which I mentioned in the textbook. And then there is a simple code about ridge regression, which you can implement. And that follows from the exercises from exercise 3 from last week. And this is roughly where I will be stopping now. And I will send an email to all of you about the meeting time when we're going to try to meet together, all of us, and so that we can discuss project 1 and also perhaps many of these exercises which you may not all have had time to look at. So I stop the recording now.